The Andromeda Galaxy, ænʻdrʒmᵻdə, also known as Messier 31, M31, or NGC 224, is a spiral galaxy approximately 780 kiloparsecs, 2.5 million light-years, from Earth. It is the nearest major galaxy to the Milky Way and was often referred to as the Great Andromeda Nebula in older texts. It received its name from the area of the sky in which it appears, the constellation of Andromeda, which was named after the mythological princess Andromeda. Andromeda is approximately 220,000 light-years across, and it is the largest galaxy of the local group, which also contains the Milky Way, the Triangulum Galaxy, and other smaller galaxies. Despite earlier findings that suggested that the Milky Way contains more dark matter and could be the largest in the grouping, the 2006 observations by the Spitzer Space Telescope revealed that Andromeda contains 1,010,12 stars, at least twice the number of stars in the Milky Way, which is estimated to be 200 to 400 billion. The mass of the Andromeda Galaxy is estimated to be 1.5 times 10^12 solar masses, while the Milky Way is estimated to be 8.5 times 10^11 solar masses. The Milky Way and Andromeda galaxies are expected to collide in 4.5 billion years, eventually merging to form a giant elliptical galaxy or perhaps a large disk galaxy. The apparent magnitude of the Andromeda Galaxy, at 3.4, is among the brightest of the Messier objects, making it visible to the naked eye on moonless nights, even when viewed from areas with moderate light pollution. Observation history. In the year 964, the Persian astronomer ænʻdrʒmᵻdə al-Sufi described the Andromeda Galaxy in his Book of Fixed Stars as a nebulous smear. Star charts of the period labeled it as the Little Cloud. In 1612, the German astronomer Simon Marius gave an early description of the Andromeda Galaxy based on telescopic observations. In 1764, Charles Messier catalogued Andromeda as Object M31 and incorrectly credited Marius as the discoverer despite it being visible to the naked eye. In 1785, the astronomer William Herschel noted a faint reddish hue in the core region of Andromeda. He believed Andromeda to be the nearest of all the great nebulae, and based on the color and magnitude of the nebula, he incorrectly guessed that it is no more than 2,000 times the distance of Sirius. In 1850, William Parsons, 3rd Earl of Rosse, saw and made the first drawing of Andromeda's spiral structure. In 1864, William Huggins noted that the spectrum of Andromeda differs from a gaseous nebula. The spectra of Andromeda displays a continuum of frequencies, superimposed with dark absorption lines that help identify the chemical composition of an object. Andromeda's spectrum is very similar to the spectra of individual stars, and from this it was deduced that Andromeda has a stellar nature. In 1885, a supernova, known as S Andromedae, was seen in Andromeda, the first and so far only one observed in that galaxy. At the time, Andromeda was considered to be a nearby object, so the cause was thought to be a much less luminous and unrelated event called the nova, and was named accordingly, Nova 1885. In 1887, Isaac Roberts took the first photographs of Andromeda, which was still commonly thought to be a nebula within our galaxy. Roberts actually mistook Andromeda and similar spiral nebulae as solar systems being formed. In 1912, Besto Slipher used spectroscopy to measure the radial velocity of Andromeda with respect to our solar system, the largest velocity yet measured, at 300 kilometers per second, 190 miles per second. Island universe. In 1917, Heber Curtis observed a nova within Andromeda. Searching the photographic record, 11 more novae were discovered. Curtis noticed that these novae were, on average, 10 magnitudes fainter than those that occurred elsewhere in the sky. As a result, he was able to come up with a distance estimate of 500,000 light-years, 3.2 times 1010 astronomical units. He became a proponent of the so-called island universes hypothesis, which held that spiral nebulae were actually independent galaxies. In 1920, the great debate between Harlow Shapley and Curtis took place concerning the nature of the Milky Way, spiral nebulae, and the dimensions of the universe. To support his claim of the Great Andromeda Nebula being, in fact, an external galaxy, Curtis also noted the appearance of dark lanes within Andromeda which resembled the dust clouds in our own galaxy, as well as historical observations of Andromeda Galaxy's significant Doppler shift. In 1922, ænʻdrʒmᵻdę presented a method to estimate the distance of Andromeda using the measured velocities of its stars. His result placed the Andromeda Nebula far outside our galaxy at a distance of about 450,000 parsecs, 1,500,000 light-years. Edwin Hubble settled the debate in 1925 when he identified extragalactic Cepheid variable stars for the first time on astronomical photos of Andromeda. These were made using the 2.5-meter, 100-in Hooker telescope, and they enabled the distance of Great Andromeda Nebula to be determined. His measurement demonstrated conclusively that this feature is not a cluster of stars and gas within our own galaxy, but an entirely separate galaxy located a significant distance from the Milky Way. In 1943, Walter Baade was the first person to resolve stars in the central region of the Andromeda Galaxy. Baade identified two distinct populations of stars based on their metallicity, naming the young, high-velocity stars in the disk type 1 and the older, red stars in the bulge type 2. This nomenclature was subsequently adopted for stars within the Milky Way and elsewhere. The existence of two distinct populations had been noted earlier by Jan Oort. Baade also discovered that there were two types of Cepheid variables, which resulted in a doubling of the distance estimate to Andromeda, as well as the remainder of the universe. In 1950, radio emission from the Andromeda Galaxy was detected by Hanbury Brown and Cyril Hazard at Jodrell Bank Observatory. The first radio maps of the galaxy were made in the 1950s by John Baldwin and collaborators at the Cambridge Radio Astronomy Group. The core of the Andromeda Galaxy is called 2C56 in the 2C Radio Astronomy Catalogue. In 2009, the first planet may have been discovered in the Andromeda Galaxy. This was detected using a technique called microlensing, which is caused by the deflection of light by a massive object. The estimated distance of the Andromeda Galaxy from our own was doubled in 1953 when it was discovered that there is another, dimmer type of Cepheid. In the 1990s, measurements of both standard red giants as well as red clump stars from the Hipparcos satellite measurements were used to calibrate the Cepheid distances, formation and history. Andromeda Galaxy was formed roughly 10 billion years ago from the collision and subsequent merger of smaller proto-galaxies. This violent collision formed most of the galaxy's metal-rich galactic halo and extended disk. During this epoch, star formation would have been very high, to the point of becoming a luminous infrared galaxy for roughly 100 million years. Andromeda and the Triangulum Galaxy had a very close passage 2 to 4 billion years ago. This event produced high levels of star formation across the Andromeda Galaxy's disk, even some globular clusters, and disturbed M33's outer disk. Over the past 2 billion years, star formation throughout Andromeda's disk is thought to have decreased to the point of near inactivity. There have been interactions with satellite galaxies like M32, M110, or others that have already been absorbed by Andromeda Galaxy. These interactions have formed structures like Andromeda's giant stellar stream. A galactic merger roughly 100 million years ago is believed to be responsible for a counter-rotating disk of gas found in the center of Andromeda, as well as the presence there of a relatively young, 100 million years old, stellar population. Distance estimate. At least 4 distinct techniques have been used to estimate distances to the Andromeda Galaxy. In 2003, using the infrared surface brightness fluctuations, ISBF, and adjusting for the new period luminosity value and a metallicity correction of -0.2 mag. Dex-1 in OH, an estimate of 2.57 plus or minus 0.06 million light-years, 1.625 times 1011 plus or minus 3.8 times 109 astronomical units, was derived in 2004 using the Cepheid variable method. The distance was estimated to be 2.51 plus or minus 0.13 million light-years, 770 plus or minus 40 kpc. In 2005, an eclipsing binary star was discovered in the Andromeda Galaxy. The binary is 2 hot blue stars of types O and B. By studying the eclipses of the stars, astronomers were able to measure their sizes. Knowing the sizes and temperatures of the stars, they were able to measure their absolute magnitude. When the visual and absolute magnitudes are known, the distance to the star can be measured. The stars lie at a distance of 2.52 times 10^6 plus or minus 0.14 times 10 to the 6 light-years. 1.594 times 1011 plus or minus 8.9 times 109 astronomical units, and the whole Andromeda Galaxy at about 2.5 times 10 to the 6 light-years, 1.6 times 1011 astronomical units. This new value is in excellent agreement with the previous independent Cepheid-based distance value. In 2005, using the tip of the red giant branch (TRGB) method, the distance was estimated to be 2.56 times 10^6 plus or minus 0.08 times 10^6 light-years, 1.619 times 1011 plus or minus 5.1 times 109 astronomical units. Averaged together, these distance estimates give a value of 2.54 times 10^6 plus or minus 0.11 times 10 to the 6 light-years, 1.606 times 1011 plus or minus 7.0 times 109 astronomical units. And, from this, the diameter of Andromeda at the widest point is estimated to be 220 plus or minus 3 kly, 67,450 plus or minus 920%. Applying trigonometry, angular diameter. This is equivalent to an apparent 4.96 degrees angle in the sky. Mass and luminosity estimates equals mass estimates for the Andromeda Galaxy's halo, including dark matter, give a value of approximately 1.5 times 1012 m, or 1.5 trillion solar masses, compared to A times 1011 m for the Milky Way. This contradicts earlier measurements that seem to indicate that Andromeda Galaxy and the Milky Way are almost equal in mass. Even so, Andromeda Galaxy's spheroid actually has a higher stellar density than that of the Milky Way, and its galactic stellar disk is about twice the size of that of the Milky Way. The total stellar mass of Andromeda Galaxy is estimated to be between 1.1 times 1011 m, i.e., around twice as massive as that of the Milky Way, and 1.5 times 1011 m, with around 30% of that mass in the central bulge, 56% in the disk, and the remaining 14% in the halo. In addition to it, Andromeda Galaxy's interstellar medium contains at least around 7.2 times 109 m in the form of neutral hydrogen, at least 3.4 times 108 m as molecular hydrogen within its innermost 10 kiloparsecs, and 5.4 times 107 m of dust. Andromeda Galaxy is surrounded by a large and massive halo of hot gas that is estimated to contain half the mass of the stars in the galaxy. The nearly invisible halo stretches about 1 million light-years from its host galaxy, halfway to our Milky Way galaxy. Simulations of galaxies indicate the halo formed at the same time as the Andromeda Galaxy. The halo is enriched in elements heavier than hydrogen and helium, formed from supernovae, and its properties are the expected on a galaxy that lies in the green valley of the color magnitude diagram. See below. The supernovae erupt in Andromeda Galaxy's star-filled disk and eject these heavier elements into space. Over Andromeda Galaxy's lifetime, nearly half of the heavy elements made by its stars have been ejected far beyond the galaxy's 200,000 light-year diameter stellar disk. Luminosity equals. Andromeda Galaxy appears to have significantly more common stars than the Milky Way, seeming to predominate the old stars with ages greater than 7 times 109 years. The estimated luminosity of Andromeda Galaxy, approximately 2.6 times 1010 L, is about 25% higher than that of our own galaxy. However, the galaxy has a high inclination as seen from Earth, and its interstellar dust absorbs an unknown amount of light, so it is difficult to estimate its actual brightness, and other authors have given other values for the luminosity of the Andromeda Galaxy, including to propose it is the second brightest galaxy within a radius of 10 megaparsecs of the Milky Way, after the Sombrero Galaxy, with an absolute magnitude of around -22.21. A close an estimation done with the help of Spitzer Space Telescope published in 2010 suggests an absolute magnitude, in the blue, of -20.89. That with a color index of +0.63 translates to an absolute visual magnitude of -21.52, compared to -20.9 for the Milky Way, and a total luminosity in that wavelength of 3.64 times 1010 L. The rate of star formation in the Milky Way is much higher, with Andromeda Galaxy producing only about 1 solar mass per year compared to 3 to 5 solar masses for the Milky Way. The rate of supernovae in the Milky Way is also double that of Andromeda Galaxy. This suggests that the latter once experienced a great star formation phase, but is now in a relative state of quiescence, whereas the Milky Way is experiencing more active star formation. Should this continue, the luminosity in the Milky Way may eventually overtake that of Andromeda Galaxy. According to recent studies, like the Milky Way, the Andromeda Galaxy lies in what in the galaxy color magnitude diagram is known as the Green Valley, a region populated by galaxies in transition from the blue cloud, galaxies actively forming new stars, to the red sequence, galaxies that lack star formation. Star formation activity in Green Valley galaxies is slowing as they run out of star-forming gas in the interstellar medium. In simulated galaxies with similar properties, star formation will typically have been extinguished within about 5 billion years from now, even accounting for the expected short-term increase in the rate of star formation due to the collision between Andromeda Galaxy and the Milky Way structure. Based on its appearance in visible light, the Andromeda Galaxy is classified as an S/B galaxy in the Dvořákov's Sandage extended classification system of spiral galaxies. However, data from the 2MASS survey showed that Andromeda is actually a barred spiral galaxy, like the Milky Way, with the Andromeda's bar oriented along its long axis. In 2005, astronomers used the Keck telescopes to show that the tenuous sprinkle of stars extending outward from the galaxy is actually part of the main disk itself. This means that the spiral disk of stars in the Andromeda Galaxy is 3 times larger in diameter than previously estimated. This constitutes evidence that there is a vast, extended stellar disk that makes the galaxy more than 220,000 light-years, 67,000%, in diameter. Previously, estimates of the Andromeda Galaxy's size ranged from 70,000 to 120,000 light-years, 21,000 to 37,000%. Across the galaxy is inclined an estimated 77 degrees relative to the Earth, where an angle of 90 degrees would be viewed directly from the side. Analysis of the cross-sectional shape of the galaxy appears to demonstrate a pronounced S-shaped warp, rather than just a flat disk. A possible cause of such a warp could be gravitational interaction with the satellite galaxies near the Andromeda Galaxy. The galaxy M33 could be responsible for some warp in Andromeda's arms, though more precise distances and radial velocities are required. Spectroscopic studies have provided detailed measurements of the rotational velocity of the Andromeda Galaxy as a function of radial distance from the core. The rotational velocity has a maximum value of 225 km per second, 140 miles per second, at 1300 light-years, 82 million astronomical units, from the core, and it has its minimum possibly as low as 50 km per second, 31 miles per second, at 7,000 light-years, 440 million astronomical units, from the core. Further out, rotational velocity rises out to a radius of 33,000 light-years, 2.1 times 109 astronomical units, where it reaches a peak of 250 km per second, 160 miles per second. The velocities slowly decline beyond that distance, dropping to around 200 km per second, 120 miles per second, at 80,000 light-years, 5.1 times 109 astronomical units. These velocity measurements imply a concentrated mass of about 6 times 109 m in the nucleus. The total mass of the galaxy increases linearly out to 45,000 light-years, 2.8 times 109 astronomical units. Then, more slowly beyond that radius, the spiral arms of the Andromeda Galaxy are outlined by a series of H2 regions, first studied in great detail by Walter Baade and described by him as resembling beads on a string. His studies show 2 spiral arms that appear to be tightly wound, although they are more widely spaced than in our galaxy. His descriptions of the spiral structure, as each arm crosses the major axis of the Andromeda Galaxy, are as follows: Section pp 1062, Section pp 92. Since the Andromeda Galaxy is seen close to edge-on, it is difficult to study its spiral structure. Rectified images of the galaxy seem to show a fairly normal spiral galaxy, exhibiting 2 continuous trailing arms that are separated from each other by a minimum of about 13,000 light-years, 820 million astronomical units, and that can be followed outward from a distance of roughly 1,600 light-years, 100 million astronomical units, from the core. Alternative spiral structures have been proposed, such as a single spiral arm or a flocculent pattern of long, filamentary, and thick spiral arms. The most likely cause of the distortions of the spiral pattern is thought to be interaction with galaxy satellites M32 and M110. This can be seen by the displacement of the neutral hydrogen clouds from the stars. In 1998, images from the European Space Agency Infrared Space Observatory demonstrated that the overall form of the Andromeda Galaxy may be transitioning into a ring galaxy. The gas and dust within the galaxy is generally formed into several overlapping rings, with a particularly prominent ring formed at a radius of 32,000 light-years, 2.0 times 109 astronomical units, 10 kiloparsecs, from the core, nicknamed by some astronomers the Ring of Fire. This ring is hidden from visible light images of the galaxy because it is composed primarily of cold dust, and most of the star formation that is taking place in the Andromeda Galaxy is concentrated there. Later studies with the help of the Spitzer Space Telescope showed how Andromeda Galaxy's spiral structure in the infrared appears to be composed of two spiral arms that emerge from a central bar and continue beyond the large ring mentioned above. Those arms, however, are not continuous and have a segmented structure. Close examination of the inner region of the Andromeda Galaxy with the same telescope also showed a smaller dust ring that is believed to have been caused by the interaction with M32 more than 200 million years ago. Simulations show that the smaller galaxy passed through the disk of the Andromeda Galaxy along the latter's polar axis. This collision stripped more than half the mass from the smaller M32 and created the ring structures in Andromeda. It is the coexistence of the long-known large ring-like feature in the gas of Messier 31, together with this newly discovered inner ring-like structure, offset from the barycenter, that suggested a nearly head-on collision with the satellite M32, a milder version of the cartwheel encounter. Studies of the extended halo of the Andromeda Galaxy show that it is roughly comparable to that of the Milky Way, with stars in the halo being generally metal-poor, and increasingly so with greater distance. This evidence indicates that the two galaxies have followed similar evolutionary paths. They are likely to have accreted and assimilated about 100 to 200 low-mass galaxies during the past 12 billion years. The stars in the extended halos of the Andromeda Galaxy and the Milky Way may extend nearly one-third the distance separating the two galaxies. Nucleus M31 is known to harbor a dense and compact star cluster at its very center. In a large telescope, it creates a visual impression of a star embedded in the more diffuse surrounding bulge. In 1991, the Hubble Space Telescope was used to image Andromeda Galaxy's inner nucleus. The nucleus consists of two concentrations separated by 1.5 parsecs, 4.9 light-years. The brighter concentration, designated as P1, is offset from the center of the galaxy. The dimmer concentration, P2, falls at the true center of the galaxy and contains a black hole measured at 3 to 5 times 107 m in 1993, and at 1.1 to 2.3 times 108 m in 2005. The velocity dispersion of material around it is measured to be approximately equals 160 km per second. It has been proposed that the observed double nucleus could be explained if P1 is the projection of a disk of stars in an eccentric orbit around the central black hole. The eccentricity is such that stars linger at the orbital apocenter, creating a concentration of stars. P2 also contains a compact disk of hot, spectral class A stars. The A stars are not evident in radar filters, but in blue and ultraviolet light they dominate the nucleus, causing P2 to appear more prominent than P1. While at the initial time of its discovery it was hypothesized that the brighter portion of the double nucleus is the remnant of a small galaxy, cannibalized by Andromeda Galaxy. This is no longer considered a viable explanation, largely because such a nucleus would have an exceedingly short lifetime due to tidal disruption by the central black hole. While this could be partially resolved if P1 had its own black hole to stabilize it, The distribution of stars in P1 does not suggest that there is a black hole at its center. Discrete sources. Apparently, by late 1968, no X-rays had been detected from the Andromeda Galaxy. A balloon flight on October 20, 1970, set an upper limit for detectable hard X-rays from the Andromeda Galaxy. Multiple X-ray sources have since been detected in the Andromeda Galaxy, using observations from the European Space Agency (ESA), ænʻdrʒmᵻdə Orbiting Observatory. Robert and Barnard et al. Hypothesized that these are candidate black holes are neutron stars, which are heating incoming gas to millions of kelvins and emitting X-rays. The spectrum of the neutron stars is the same as the hypothesized black holes, but can be distinguished by their masses. There are approximately 460 globular clusters associated with the Andromeda Galaxy. The most massive of these clusters, identified as Male 2, nicknamed Globular 1, has a greater luminosity than any other known globular cluster in the local group of galaxies. It contains several million stars, and is about twice as luminous as Omega Centauri, the brightest known globular cluster in the Milky Way. Globular 1, or G1, has several stellar populations and a structure too massive for an ordinary globular. As a result, some consider G1 to be the remnant core of a dwarf galaxy that was consumed by Andromeda in the distant past. The globular with the greatest apparent brightness is G76, which is located in the southwest arm's eastern half. Another massive globular cluster, named 037b327 and discovered in 2006 as is heavily reddened by the Andromeda Galaxy's interstellar dust, was thought to be more massive than G1 and the largest cluster of the local group. However, other studies have shown it is actually similar in properties to G1. Unlike the globular clusters of the Milky Way, which show a relatively low age dispersion, Andromeda Galaxy's globular clusters have a much larger range of ages, from systems as old as the galaxy itself to much younger systems, with ages between a few hundred million years to 5 billion years. In 2005, astronomers discovered a completely new type of star cluster in the Andromeda Galaxy. The newfound clusters contain hundreds of thousands of stars, a similar number of stars that can be found in globular clusters. What distinguishes them from the globular clusters is that they are much larger, several hundred light-years across, and hundreds of times less dense. The distances between the stars are, therefore, much greater within the newly discovered extended clusters. In 2012, a microquasar, a radio burst emanating from a smaller black hole, was detected in the Andromeda Galaxy. The progenitor black hole is located near the galactic center and has about 10 m. Begin small matrix m_odo end small matrix. Discovered through a data collected by the European Space Agency ænʻdrʒmᵻdə probe, and subsequently observed by NASA's Swift Gamma Ray Burst mission and Chandra X-ray Observatory. The Very Large Array, and the Very Long Baseline Array. The microquasar was the first observed within the Andromeda Galaxy and the first outside of the Milky Way galaxy. Satellites. Like the Milky Way, the Andromeda Galaxy has satellite galaxies, consisting of 14 known dwarf galaxies. The best known and most readily observed satellite galaxies are M32 and M110. Based on current evidence, it appears that M32 underwent a close encounter with the Andromeda Galaxy in the past. M32 may once have been a larger galaxy that had its stellar disk removed by M31, and underwent a sharp increase of star formation in the core region, which lasted until the relatively recent past. M110 also appears to be interacting with the Andromeda Galaxy, and astronomers have found in the halo of the latter a stream of metal-rich stars that appear to have been stripped from these satellite galaxies. änʻdrʒmᵻdę does contain a dusty lane, which may indicate recent or ongoing star formation. In 2006, it was discovered that 9 of the satellite galaxies lie in a plane that intersects the core of the Andromeda Galaxy. They are not randomly arranged as would be expected from independent interactions. This may indicate a common tidal origin for the satellites. Collision with the Milky Way. The Andromeda Galaxy is approaching the Milky Way at about 110 km per second, 68 miles per second. It has been measured approaching relative to our Sun at around 300 km per second, 190 miles per second. As the Sun orbits around the center of our galaxy at a speed of approximately 225 km per second, 140 miles per second. This makes the Andromeda Galaxy one of about 100 observable blue-shifted galaxies. Andromeda Galaxy's tangential or sideways velocity with respect to the Milky Way is relatively much smaller than the approaching velocity, and therefore it is expected to directly collide with the Milky Way in about 4 billion years. A likely outcome of the collision is that the galaxies will merge to form a giant elliptical galaxy or perhaps even a large disk galaxy. Such events are frequent among the galaxies in galaxy groups. The fate of the Earth and the Solar System in the event of a collision is currently unknown. Before the galaxies merge, there is a small chance that the Solar System could be ejected from the Milky Way or join the Andromeda Galaxy. Amateur observing. The Andromeda Galaxy is bright enough to be seen with the naked eye, even with some light pollution. Andromeda is best seen during autumn nights in the northern hemisphere, when from mid-latitude the galaxy reaches zenith and can be seen almost all night. From the southern hemisphere, it is a springtime object and does not reach a high altitude over the northern horizon, thus making it difficult to observe. Binoculars can reveal some larger structures and its 2 brightest satellite galaxies, M32 and M110. An amateur telescope can reveal Andromeda's disk, dark dust lanes, the large star cloud NGC 206, and even some of its brightest globular clusters. See also Andromeda Nebula in fiction. List of Messier objects. List of galaxies. New General Catalogue. NGC 206, the brightest star cloud in the Andromeda Galaxy. Notes. The Andromeda Galaxy on Wikiski. DSS2. SDSS. GALEX. Iris. Hydrogen alpha. X-ray. Astrophoto. Sky map. Articles and images. Stardate. M31 fact sheet. Simbad data on M31. Messier 31. SEDS Messier pages. Astronomy picture of the day. A giant globular cluster in M31 1998 October 17. M31. The Andromeda Galaxy 2004 July 18. Andromeda Island Universe 2005 December 22. Andromeda Island Universe 2010 January 9. WISE Infrared Andromeda 2010 February 19. M31 and its central nuclear spiral. Amateur photography. M31. Globular clusters in M31 at the Kirdridge Observatory. First direct distance to Andromeda minus Astronomy magazine article. Andromeda Galaxy at Sol Station. Com. Andromeda Galaxy at the Encyclopedia of Astrobiology, Astronomy, and Spaceflight. M31. The Andromeda Galaxy at Night Ski Info. Com. Than. Kerr. January 23, 2006. Strange setup. Andromeda satellite galaxies all lined up. Space. Com. Hubble finds mysterious disk of blue stars around black hole. Hubble observations. September 20, 2005. Put the mass of the Andromeda core black hole at 140 million solar masses. M31. Apparent novae page. IAU. Multi-wavelength composite. Andromeda project. Crowdsource. Gray, Megan. Zymanek, Nick. Merrifield, Michael. M31 Andromeda Galaxy. Deep Sky Videos. Brady Harron. Andromeda Galaxy. M31. At Constellation Guide. APOD 2013 August 1. M31's angular size compared with full moon. Hubble's high-definition panoramic view of the Andromeda Galaxy. National Geographic. Com video of the Hubble high-definition panoramic view of the Andromeda Galaxy.